So in this lecture I will be reviewing Gas Law Quiz 2 problem that I wrote for you as a review for the second Gas Law quiz. So let's get started. So hopefully that's going to be a key that's written smaller. Okay, so here's the key, hopefully. Alright, so given the following manometer with water as a liquid inside. So wow, I'm telling you that. And that tells me two different things. In fact, that screams to me, okay, when there's water inside, there's two things it tells me right away. Number one, it tells me that the gas that I have is with water vapor. Why? Because if this is water, water is always evaporating. So if it's evaporating, it's adding some gas molecules to the gas already in here. So it tells me it's with water. It means I have water with the chemical. There's a mixture. And that means if I want to just get the pressure of CH4, I'm going to have to do a Dalton's law problem. I'm going to have to subtract away the other gas, okay, or know the totals or the individual partial pressures. Okay, it's the first thing it tells me. The second thing it tells me is that to evaluate the total pressure in here, and I need the total pressure before I can evaluate or get one of the gases, I'm going to have to change this height of liquid being supported in water to density. So we're going to have to convert the H2O height into mercury height because that's a pressure equivalent to do the problem. So let's get started. The first part is the manometer part of the problem. Okay, what's the manometer part? Well, I need the total pressure. If I'm after just the methane, I'm going to need the total pressure. And since I know that the water evaporating is tied to a certain temperature that I can get from tablature, can you go with me? The angel sound? La. Okay, go la from a table. Okay, we get that from a book. And we can measure the partial pressure of the water just from the table. But in order to get the CH4, I need the total pressure. So the manometer is going to help me do that and evaluate the pressure from the atmosphere. So looking at the manometer, I see that the gas is losing by 30 millimeters of water. We have the atmospheric pressure pushing back on the gas here, and it's supporting a column of water plus the pressure. Okay, so in any case, the gas in here is losing by these 30 millimeters. So all I need to do is take the atmospheric pressure, and with this height of the column, since this is losing by this amount being supported, I'm going to subtract by the atmospheric pressure. So this is the manometer part of the problem. But my first problem is that this height here is millimeters of water, and that's not a pressure equivalent. I need to convert that to torr or millimeters of mercury. So very simple. I start with height times density equals height times density. If you want to write it out, you can. And you would take your 30.0 millimeters of your water. You would times it by the density of water. Since I didn't tell you otherwise, the density is 1 gram per milliliter. Okay, now we're going to solve for the height of mercury. That density goes below, and for mercury, that density is 13.6 grams per milliliter. And we can see that the height in mercury is going to be, the units cancel, we're left with millimeters. So when we do this, okay, and I take my 30 and divide it by 13.6, I get 2.206. 2.206, and that of course is millimeters of mercury. Of course, that is also torr. Same thing. No big deal. Been down that road before. So that's an important number. So what does that represent? That represents the amount of pressure it takes to support this column. All right. So if the atmospheric pressure is supporting using part of its pressure to support this column, the rest of its force is pushing back on this gas. That's why you subtract. Now, I'm going to subtract this from the total pressure pushing down over here. Well, the total pressure is 101.0 kilopascals. For those that don't have it, I made a mistake. This is actually 101.0 kilopascals. So if you're following along with me and you didn't realize I made that mistake, I feel bad. Now I'm over it. This is the unit we're going to use now. So yours might read something different. We're using 101.0 kilopascals. Now, 101.0 kilopascals is not in torr, so I'm going to have to convert. And that's easy. kPa on the bottom, because I want to get rid of it. I want torr up top. What's the converting units? Well, you should know this now. 101.3 kilopascals standard pressure and 760 torr, the height of a column of mercury at sea level. All right, and we do this, and we solve. Okay, 101 times 760. Divide by 101.3, and I get 757. I don't know, we'll just one decimal place here. 0.7, and of course is torr. It's another important number. That's the total atmospheric pressure. So my manometer question, very simple. 757.7 torr minus 2.206 torr. Well, what does that give me? I get 755.5 torr. Now, what did I just solve for? I solved for the pressure of these gases, which is pressure total, because I know it's a mixture. So my next step is to do a Dalton's law of pressure. So number 2 is we do the Dalton's law step. Now, Dalton's law, partial pressure, means that the total pressure, PT, is equal to the partial pressure of the water vapor plus the partial pressure of the methane gas. We're trying to get the methane gas. Well, now I have the pressure total. That is 755.5 torr. Make sure you're in the same units. The partial pressure of water. Well, as I said before, we go to a tablature to get that, and we know the system's at 25 degrees Celsius. So I go to my table, and at 25 degrees Celsius, there is 23.8 torr, and that's the partial pressure. 28.3 torr. Just make sure, sometimes my short-term memory leaves me at this height. Yes, okay. See, a good thing I checked. It's 23.8. I got it backwards. I had a feeling. 23.8. Okay, torr. Okay, what's this guy? Well, what plus that equals that? Well, it's a little algebra. Essentially, you're going to subtract 23.8 from 755. Okay, so let's do that. And I get my partial pressure of my methane, dry, to be 731.7, and of course the unit is torr. And that is my answer for just the hydrogen, I'm sorry, just the methane gas, CH4. That's the partial pressure of the methane. All right, and that's essentially what you're going to be doing tomorrow. However, I'll take this a little further with you. What if I said to you, okay, how many molecules of hydrogen, how many, I'll just change this as I'm making up as on a fly here. The fly's kind of small to write on, so I won't make it on a fly. How many atoms of hydrogen are in the manometer, manometer? Okay, that could be my second question. Not sure. Well, because I'm asking for how many atoms, I know I need to go to moles here, but gosh darn it. All right, I only have his partial pressures. So how do I go to moles? Well, we know, party people, that PV equals nRT, right? So that means N is equal to PV over RT. And we could solve for the moles of H. Now, careful, careful, careful. Not only do we have methane, we have water vapor. So we're going to need to evaluate how many hydrogens are, once we have moles of methane, we're going to times that by how many number? Yeah, we're going to times that by 4. This, once we have moles of water, we times that by 2. So our first step is we'll deal with methane. All right, so let's slow down a little bit. So my second question, I'm saying how many atoms of hydrogen are there in the manometer? Okay, so my plan of attack here is to look back at my manometer and realize I have a mixture of gases. I've got methane and I got water vapor. Now, I'm going to need something extra from this. I'm going to need to know, and I didn't put this in here because I'm adding it, I'm going to know what the volume is. We're going to make this 10.0 liters. So we're going to say that the size of the container is 10 liters. Okay, so let's go attack this problem. All right, I want total number of atoms of hydrogen in the manometer. Understand we have water and we have methane. Both have hydrogen. So let's start with methane. And I'm going to start on a new page. Okay, now before I do so, I should know what the pressure of the partial pressure of the methane was. And we found the partial pressure to be 731.7 torr. So, don't know what happened just there. Go back, maybe. All right, yeah. So let's go here. And I guess it's just repeating itself. So let's just go to a blank page or blank part. So we have 731.7 torr. So 731 point, my short-term memory is going. Sorry, guys. I know you scream at 0.7 torr. That's the partial pressure of the methane. Okay, now I have 23.8 torr. And that's the partial pressure of the water. Okay, I know that this is 10 liters. Okay, so now we're going to rock on and continue this. So let's start with the methane. Put that in black. So PV equals nRT, which means N is equal to PV over RT. I'm going to solve for the moles of methane molecules. So the pressure, partial pressure is 731.7 torr. The volume is 10 liters. Okay. The R is 6236 torr liters mole kelvins. Okay, now if you wanted to use 0.08206 atmospheres liters mole kelvins, this would have to be in atmospheres. I would give you both of those constants. I know some people know them. Right, Brandy? Any case, temperature. Temperature, of course, is in Kelvin, and the temperature of our system, I forget, let's look up here, was 25 degrees Celsius. Remember, we added that to 273. Okay, and that is 5 and 3 is 8, 298, right? Making sure my math is right. Sometimes I'm going to fix it. 298 Kelvin. All right, and I should get moles from this. Torr cancels, liter cancels, Kelvin cancels, and 1 over mole is going to be moles. So let's go find that number. Calculator. 731.7 times 10. Divide by 62.36. Oh, I made a mistake. I got to put that in parentheses. So 731.7 times 10. Divide by, in parentheses, 62.36 times 298. Close my parentheses. Okay, I get my moles to be 0.3937 moles. And that's, of course, of methane molecules. So take my 0.3937 moles of methane molecules, and look what I'm going to do here. The question was how many H atoms. Well, isn't there 4 H's per one of these molecules? So watch, I'm going to get rid of methane. For every one of these, there's 4 H's, right? H atoms, right? I'll just leave that H right there. And of course, that would times my moles by 4 because there's 4 H's per one of these. And then because I was asking for the actual number, we're going to use Avogadro's number. Get rid of mole. For every 1 mole, I have 6.02 times 10 to the 23 number of atoms. Okay, just check to make sure I did this right. Moles cancel. Okay, methane cancels. And I have H atoms, so that looks good. Let's put it in our calculator. So I get 9, oops, I did a darker number. I get 9.48 times 10 to the 23. All right, and that of course is H atoms. But we know that's only from the what? The methane. So let's just highlight that to remind us that's the H atoms from the methane. Okay, but we want the water. So we do the same thing for the water because we're going to add them together. So we do water, and we know that N is equal to PV over RT. And we know the pressure is equal to, what is it, 23.8. That was from the tables. Okay, and that's torr. The volume, still 10 liters, because both gases were flying around in 10 liters. It's a big mistake people make. They think that they take up a partial volume. No, they actually fly around the total volume, so it's 10 liters. The universal gas constant in torr, 6236 torr liter mole Kelvin. Of course, you'll be given that constant. And the temperature is still 298. They had the same temperature and pressure. Let's go find that moles. Okay, put that in my calculator. I'm really fast, I guess. 0.0128, or I pause it and then do it to make myself impressive. And that's, of course, moles. And that's going to be lower than the moles I got here. This should be, because most of this should be what? Methane. Only a little bit evaporates. It's not that much pressure, right? That's the partial pressure. It's small. And of course, the other one is much higher. So it should be a small amount. Now, that's moles of what? H2O molecules. We want atoms of H's. So same thing. We take our 0.028 moles of water molecules. And I know for every one H2O, there is 2 what? H atoms. Although I don't want to write H atoms, I don't know why I keep doing that there. You can. Okay, 2 H atoms, or 2 hydrogens. And of course, once we have moles of H, we're going to get rid of this mole here. So 1 mole is equal to 6.02 times 10 to the 23 number of atoms. All right, and we'll put this in our calculator. Okay, so I get 3.08 times 10 to the 22nd number of atoms. It's a far lower number than this because it's a smaller number of moles. Okay, and of course this is an important number. This is the number of atoms of what? H's from the water. And this is the H's from the methane, CH4. So we're going to add these two numbers together. Okay. And what we're going to get, party people, put these in our calculator. Let's do it. Okay, so I get 9.79, I feel like one of those cooking shows, all of a sudden I'm done, times 10 to the 23rd. Okay, and that's H atoms total. If you notice, this number didn't change all that much because I'm adding this big number by a smaller number. This is smaller by a 10 times, right? It's like 9.48 plus 0.3, right? This differs by a tenth. So 9.8 times 0.3, that's why it's 3 plus 4 is 7, okay? And that, of course, is the number of hydrogen atoms. Hopefully you followed that. All right, and that's all fair game. Now, it may or may not be hydrogen atoms tomorrow. Maybe it'll just be the carbon, and that's a lot easy, right? But who knows? Okay. The other thing I could do tomorrow is say, hey, what if the manometer sprung a leak? What if this sprung a leak? What's the rate of effusion? Well, I know that let's say the rate of effusion between, let's say, Cl2 and water. It's the rate of effusion. If it sprung a leak, the faster gas is going to effuse better. But what's the ratio? Well, that's Graham's law. The rate of one gas over the rate of the second gas is equal to the rate of effusing or diffusing into the room is equal to the inverse of its mass, square root of the inverse of its mass. M1, M2. Notice these are inverse. So if I plug this in, Cl2 over H2O equals, okay, what's the mass of water? 18, right? And Cl2 is 70. Now where am I getting that? There's 2 Cl's in Cl2, right? So 2 Cl's, 2 times 35. I'm getting this from the periodic table. It's the relative atomic mass. That gives me 70. And then we got the water. Water is what? 2 H's, which would be 2 times 1, that's the atomic mass, is 2. And then, of course, you'd add that 2 to 1 oxygen, which is 1 times 16. So 16 plus 2, this would give you 18 grams per mole, and that'd go up there. So we would take 18 divided by 70. That gives me, let's just rewrite it over here, square root of 0.2571. So I'm going to take the square root of that number. And I get an answer that equals, well, I'm not sure if I agree with that answer. Let me just do it one more time. The square root of 0.2571. Okay, so and then the answer is 0.507. And what does this mean? This means that chlorine effuses 0.507 times that of water, which means it almost goes half as fast. Or you can think of water, if you do the inverse of that, x to the negative 1. X to the negative 1 means it's 1.97. So that would mean that almost 2, or water, escapes the opening twice as fast. Okay? So those are the types of questions you can see. Obviously, I'm going to have another question in there. I think a Dalton's law of partial pressure question. So I would definitely look at question number 3 of Graham's law. I'm sorry, of the partial pressure. Look at question number 3 of the Dalton's law of partial pressure ditto. Okay.